Okay, this is Mac 1105, Chapter 4, Section 4, Quadratic Functions. This is going to be a short video because this is just going to deal with going over to word problems. This is looking at, if you look at the title of the section, it says Building Quadratic Models from Verbal Descriptions and Data. So models, make sure you understand that models in math means equations. So that's what we're going to do. All right. So to begin with, up here at the top, it says an economic revenue, which is capital R, in dollars, is defined as the amount of money received from the sale of an item and is equal to the unit's selling price, P, in dollars, of the item times the number of X units actually sold. That is, R, revenue, equals number of items times the price. The law of demand states that P and X are inversely related. So, as one increases, the other decreases. Okay, so we've already talked about inverse relationships. The equation that relates P and X is called a demand equation. When a demand equation is linear, the revenue model is a quadratic function. All right, so here's what we have. It says the marketing department at Texas Instruments has found that when certain calculators are sold at a price P, dollars per unit, the number X of calculators sold is given by the demand equation of X, the number of calculators, equals 21,000 minus 150 times the price. Okay. Part A says, find a model that expresses the revenue as a function of the price. So what they do here is we're looking at revenue equals X times P. Now remember, we already know what X is. So we're going to put 21,150P in place of X, multiply times P. And that's how we get this negative 150P squared plus 21,000P. So you see what's happening here. In this problem here, they've redefined X as 21,000 minus 150P based on the price. So all we've done is taken this and replaced it in X in this equation. And then multiplied by P. Now we have a quadratic because we can see the P highest powers to square. Letter B says, what is the domain of R? Assume revenue is non-negative. Well, look. If we look at this right here, think about our domain of problems. Basically, if we're looking at the domain, then we have to understand that 0, everything has to be greater than or equal to 0. Because it states in the problem up here, letter B, that revenue is non-negative. So we're starting at 0. So basically what we do is if we set the equation we have there at 21,000 minus 150P greater than or equal to 0 and then solve, then what happens is we get P is less than or equal to 140. So there's our domain. It's between 0 and 140. So we got the 0 because we know we can't have a negative number of calculators sold. No such thing. We got the 140 because what we did was take the number of the equation for the number of calculators sold and set it greater than or equal to 0. So we want to know what the maximum amount of calculators or maximum price is in terms of these calculators. That's how we got that. If we go to letter C, it says what unit price should be used to maximize revenue? Well, we come down here to letter C, and basically what we're going to do is use, P is our X in this problem. So see, we learned from the previous chapter that we can do negative B over 2A. All right? And so what happens here is if we look at our quadratic equation, which is right here, this is A, this is B, we don't have a C. So you see how they're getting 21,000, which is B, or I should say negative 21,000, over 2 times negative 150. Negative 150 is the A. Do the math and we find out that the what the question was asking is, what is the unit price that should maximize revenue? Well, that unit price is $70. We come to letter D. It says if this price is charged, what is the maximum revenue? Well, what we're going to do is take that $70 and put it in back into our equation. This is what we've been doing. This is our X from the previous chapter. It's P, it's price. If we get price, we can substitute it in the equation, do the math, and we find out we're going to have a total revenue of $735,000. So, in general mathematics terms, this is X, we're finding Y. So this right here, this 70 and this 735,000 is an ordered pair. It is the maximum, or the vertex, for a parabola. And remember, we know that in terms of this is a parabola that goes down because it's negative. So 70, 735,000 is the vertex. It's the maximum point, which tells us the maximum price we want to charge to get the maximum revenue. If we come up here, letter E says how many units are sold at this price. Well, we got to do is 670 back into the formula for X. Now remember, X, this is the formula for how many units are sold. X is how many units are sold. All we do is stick the 70 back in there. We find out 10,500 units are sold. It wants us to graph R. So we come over to this page. Here's the graph of R. Notice they made the y-axis from 0 to 800,000, because remember, we know the maximum is at 735,000. Notice they made the x-axis from 0 to 140, because we know the maximum price we can charge is $140. In terms of letter G, let's look at letter G. All right, letter G says, what price should Texas Instruments charge to collect at least $675,000 in revenue? Well, we got two ways we can solve this. We can use the equation. We can put $675,000 in for the R sub P. Then all we're going to do is, add this over, subtract this over. The reason we add this over is because in a trinomial we always want the square term to be positive. Then we can factor out 15, or I guess 150. This gives us this factors into this, and if we substitute these values in, we can see that we can charge a minimum price of 50 or a maximum price of 90 to get a revenue of 675,000. We could also look at this. If we're looking for a maximum revenue of 675,000, we could go to the graph, draw a straight line, and we get 50 and 90. Two different ways to get the same answer. All right, here's the second word problem. So it says a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So here's the diagram here. Okay, there's our two widths, our two lengths. Now if we look at this, they're using X as length, W as W. So 2 times length plus 2 times W equals 2,000. This is our perimeter equation. The area of a rectangle is A equals L times W, but remember we replaced L with X. Okay? So now what happens is that we're going to take the perimeter equation. We're going to subtract the 2x over, then divide by 2, and we get width is equal to 1,000 minus x. So what we're going to do is take 1,000 minus x, and substitute into W for area, because remember, we're looking for the maximum area. What happens here is we go x times 1,000 minus x, we get negative x squared plus 1,000x. So then what happens is we can do our negative b over 2a. Our a is negative 1, our b is 1,000. Substitute that in, we get 500 for x. And remember, x is our length. So the maximum length we want is 500. if we take that 500 and put it back into the equation right there, in other words, put x here and put x here and put x here, which is what they did here, we find out that the maximum area is going to be 250,000. So the largest rectangle that can be enclosed by 2,000 yards of fence has an area of 250,000 square yards, and its dimensions are 500 yards by 500 yards. How they got the other 500 yards for width was they just took 250,000 and divided by 500.